Alright guys, continuing on with our test review. This one is question number 12. So let's take a look at what we've been given and what we're trying to find here. So it looks like we've been given 277 volts on the phase, and this is our alternator, that's our source. So this guy right here is our source, and we've been told that it's an alternator. And over here we've got our three-phase load. And we have to figure out whether that value is whether this load right here is a delta or a Y. So obviously right here we have our source as a Y. And we can tell that because all of these guys are connected together at the same potential there. So it has that star point or that Y connection there. If we look at this load though, there doesn't seem to be a common connection between any of these resistors here. So we have one resistor that's connected between A and C. We have another resistor here that's connected between A and B. And we have another resistor over here of equal value, so everything's balanced here. And that's connected between B and C. So at that point we can see that it's not a Y, it's got to be a delta here. So let's walk through how it is a delta. So remember from previous classes where we were going through all of our connections for the delta, there was a trick to the delta. It went A to B, B to C, and then C back to A. So these are single phase loads, but they're connected up as a delta. There's A to B, B to C, and C back to A. So that three-phase load there is connected up as a delta. Why don't we redraw that guy so it makes more sense to us, because we want to put it into that configuration that we're used to. Okay, so that guy's being fed, and now we have to find, the first thing we need to find is the line voltage output from the alternator. Okay, well, we've got a given value of 277 volts. So at the source, we have our phase voltage is equal to 277 volts, and it's a Y, so we know that the line voltage is going to be 277 times root 3, and that gives us a line voltage of 480 volts. No need to show you how to do that on the calculator now. So 277 volts on the phase, giving us a line-to-line voltage of 480 volts. Okay, so over here at this three-phase delta, we know that the voltage going in is going to be 480 volts on the line. Okay, so we'll drop that in here because we know that for certain. And now we need to find the phase voltage on this delta. Well, we know that on the delta that V line is equal to V phase, so the phase voltage is also equal to 480 volts. So the voltage right there is 480 volts. And that helps us with the next step, the value of current through each load resistor. Well, if this is 480 volts, then this voltage right here is also, maybe I'll put it in the middle here so we can see what we're doing. This voltage right here is also 480 volts on the phase. And we can clearly see our Ohm's law chart here, 480 volts divided by 16 ohms. So we'll do that over here for B, that we now can find our current on the phase of our delta because we have 480 volts being impressed across 16 ohms. Let's grab the calculator and see what that is. So we got 480 volts divided by 16 ohms, and that gives us 30 amps. Beautiful. So we got 30 amps here. And now it's a matter of finding where that 30 amps actually is. So we just found that that current was right here, right? So that 30 amps is a phase current. Or if you want, that 30 amps is right here on the phase. So you may need to redraw these resistors as a delta so you can see exactly what's going on in the circuit. I've purposely done this to screw you up. So we now found that our phase current, or the value of current through each load resistor, was 30 amps. and that was our phase current on the load. And now we got to find the current that's on each of the windings of the alternator. So our next step is to find our line current, and obviously the line current will be the same as the phase current on the Y. But most people just think that you can take that 30 amps and bring it right across, and so it's 30 amps over here. But if we take a look at this diagram, you can see that the 30 amps is on the phase. And we know that for a delta, our line current is equal to our phase current times root 3. So the line current isn't 30 amps. It's the 30 amps times root 3. So let's find out what that value is. Okay, so don't get tripped up there. The 30 amps does not come out on the line. This is the value on the inside of the delta. We need to use that and the fact that their line current is root 3 higher in order to find our line current. So what do we got? We got 30 times root 3. That gives us 51.96 amps on the line. So this value right here on the line, where are we going to put that? So that line current right there is that value right there, right? Or if you want, there's 30 amps flowing here, there's 30 amps flowing here, there's 30 amps flowing here, but on the line there is 51.96 amps on the line, which is a little bit messed up, right? There's 30 amps here and there's 30 amps here. You would think that this guy would be 60 amps, but remember that these currents do not happen at the same time. They're 120 degrees out of phase. So 30 amps times root 3 gives us 51.96 amps on the line. Now, for that guy, we've now found that our line current is 51.96, and we know that for Y, our I line is equal to I phase, which is equal to 51.96 amps. So we can see that this current on the inside of the Y is also 51.96 amps. So you can see how redrawing the circuit to make it match with the delta that's in your mind will help you to figure out your currents. And then keeping track of where the current is coming from will help you to determine what currents are on the inside and the outside of the circuit. So current in each phase winding of the alternator is going to be 51.96 amps. So the 30 amps was on the load, on the delta, and this was at the source, and that was a Y. Last thing we need to find is the kVA output of the alternator. So for the last question for D, we need to find the kVA output for the alternator for this load. So our kVA, or our VA, let's just start with VA and then we'll switch it over to kVA, is our V line times I line times root 3. So what have we found? We found that our V line was equal to 480 volts, right? And we're keeping track of all our values, so we can just quickly go back to our diagram. So we got 480 volts on the line. Our line current we determined to be 51.96 amps on the line. And then we have to multiply those guys by root 3. Okay, so what do we got? We got 480 volts. We're going to multiply that by 51.96 amps. And then we're going to multiply that by the square root of 3. That gives us 43,198.73. 43,198.73. Okay, so we can see there that our kVA output, if we're going to round up here, we got 43, basically 43.2 kVA as the required output for that three-phase load. And now again we found everything, but it was slow and methodical and took a while to do a few extra diagrams in order to work through this one. Without the chart, it's a lot harder to find all your values. Alright guys, let's move over to the next one, number 13. Alright, number 13, 3 resistance heaters our delta connected to a 480 volt three-phase supply. If each resistor has a value of 12 ohms, calculate your three-phase line current and the total power developed by the load. So we know that each of these guys is 12 ohms. That's a balanced circuit. That value that was given is our line voltage. And for the delta, we're going to write down our equations for a delta. So for a delta, it is more of a parallel circuit. So we know that V line is equal to V phase. And we know that I line is equal to, let's get rid of that, a little bit more room here. I line is equal to I phase times root 3. Okay, so let's use those to tackle these guys. Let's see. Three-phase line current. Okay, so we've always taken a three-phase circuit and we've broken it down into a single-phase circuit with Ohm's law. So this value for 480 volts on the line, well, we know that now that the phase voltage is going to be identical. So our step one here is that we know that 480 volts on the line is equal to 480 volts on the phase. So we know that this voltage right here is 480 volts on the phase. Now we've determined our three-phase, our phase current here by taking 480 divided by 12 ohms. So our second step here is to take 480 volts on the phase divided by our phase impedance of 12 ohms. And if we take 480 divided by 12, that gives us 40 amps. There's 40 amps on the inside of that delta. Okay, that's a phase current. We're going to write that value down. So that value right there is 40 amps, but it's on the phase. We know that the line current is going to be root 3 higher. So the value here is going to be our line current. So we're slowly building up to find that value for our three-phase line current. So that is going to be 40 amps on the phase times root 3. Okay, so we got 40 times the square root of 3. That gives us 69.28 amps. And that's a line value. Beautiful. So that value is there, 69.28 amps on the line. Okay, so we found the 40 amps. Our third step in order to find that final value was to take our 40 amps on the phase, multiply that by root 3, and that gave us our total line current of 69.28 amps on the line. Everything from there down was for this answer right here for A. Okay, next thing we need to do is find the total power developed by the load. Now with this one I haven't given you power factor because they're just simply resistors. So they're all in phase. So we don't have to use power factor, we're just going to use V line times I line times root 3. So in order to find the answer for B, we know that our wattage, our total wattage is going to be equal to V line times I line times root 3. So wattage and VA are the same here because they're purely resistive loads. So let's see, what's our line voltage is 480 volts on the line. Our line current we just found to be 69.28 amps. And then we're going to multiply that by root 3. Okay, so we've got 480 volts. We're going to multiply that by 69.28 amps. And then we're going to multiply that by the square root of 3. 57,598.31. Beautiful. Okay, so we can put that value up here and finish this guy off. So we got 57,598.31 watts. Beautiful, not too bad. Right? It takes a little bit of time to follow everything through. Once you've done that, then it's easy to find your values using the equations that we've been using for the past 3 weeks. All right, let's take a look at number 14, guys. 3 resistors of equal value are delta connected to a 600 volt 3-phase supply. So we know that this value right here is our line voltage, that's given. If the total power used by the load is 54 kilowatts, determine the current through each of the resistors. So I've already done this, so I'm just going to erase this out. The line current and the ohmic value for each of those resistors. All right, so not much room to work here. Let's see if we can drop everything in. Okay, so that total power there, we know that our total power is going to be equal to V line times I line times root 3. So our total power is 54,000 watts. And we're looking for the line current here. Let's start off with this guy right here. So total power is 54,000 watts. We know that our line voltage is 600 volts. We don't know what our line current is, but we do know that constant at root 3. So we have to reconfigure this equation to give us our line current. So we're going to divide by everything else other than that line current. So we're going to take our line current is equal to this 54,000 watts divided by 600 times root 3. All right, we need to eliminate the 600 volts and the root 3 in order to just get the line current. We're multiplying here, so we have to do the opposite. We're going to divide each side by 600 times root 3. And that gives us, let's find out what that is. So we got 54,000 divided by, and I'm going to put brackets here so it divides by everything. Otherwise it may divide by 600 and then multiply by root 3. So 600 times the square root of 3, close brackets. It looks like I need one more bracket there, right? And that gives me 51.96 amps. So that gives us this value right here, 51.96 amps on the line. And so we know that this value right here is 51.96 amps on the line. And now we've got to find the current through each of the resistors. Well, on the delta, so this was actually the answer for B. Now we're working our way through the answer for A, and we know that for a delta, that our V line is equal to V phase, and we know that our I line is equal to I phase times root 3. So again, in order to find our phase current, we're going to take our line current and divide by root 3. So our phase current then is equal to this 51.96 amps divided by root 3. And we've already done this on the previous question, but let's just double check that value. So we got 51.96. We're going to divide by the square root of 3. And that gives us 30 amps. Beautiful. So same values as we saw in the previous question. So the current through each of these resistors is 30 amps, and that is a phase value. So the current here is 30 amps. Last thing we need to do is find the ohmic value for each resistor. So here previously for A, we were also writing down the fact that the V line equals V phase. So our last thing for finding the C answer, not much room to work here, is that we have 600 volts on the phase. We just found that we have 30 amps flowing on the phase, right? Because this voltage right here is also 600 volts on the phase. And 600 divided by 30 is going to give us our ohmic value. 600 divided by 30, come on, gives me 20 ohms. So my resistance value, or my impedance value on the phase, is 20 ohms. Beautiful. All right, guys, let's stop there. We'll pause and we'll bring back on the next video. The next video will start in at question 15.